Okay, so let's take a look at how we find the pH of acidic solutions. And then in the next video, we will look at finding the pH in basic solutions. We're going to spend most of our time in acid-base chemistry looking at weak acids, but let's start by looking at a strong acid. Hydrochloric is a strong acid. By definition, that means if I have a solution of hydrochloric acid in water, 100% will be what we say ionized. The acids donate protons. The acid will donate a proton to water to give me H3O plus, the hydronium ion, and chlorine. 100% will do that. So let's take a quick look. So acids donate the protons. Bases accept. In this case, water is acting as a base. How can water be a base? It's a neutral compound. It can sometimes be a base, sometimes an acid. What allows water to act as a base? I've got very electronegative oxygen that has a couple of unshared pair. The proton that's coming off of HCl, proton H+, can attach to either one of these. When that happens, this now has added an H+, so this whole thing is positively charged, hydronium. So in this case, water is acting as the base. We say hydronium is the conjugate acid, and chloride is the conjugate base. Those are terms we mostly use for equilibrium situations for weak acids, but it can apply here too. After HCl has donated its proton, what's left? The chloride ion. So if there were a reverse reaction, in this case there's not, that proton would go back. But the chloride ion will not act as a base. But we would still say the chloride ion is the conjugate base of hydrochloric acid. But it's not a base. Now, because of this, that 100% will be ionized, we can directly find the pH if I know the concentration of the acid. So, let me erase just this. If I've got the concentration of the acid, so what does that say? I have 0.850 molar HCl. 100% of that 0.850 moles per liter will do that. Therefore, what is my concentration? 0.850 molar of hydronium. And it's also 0.85 molar of chloride, but we don't care about that when we're finding the pH. So if you're given a problem like this, 100% does that. And then we want the pH. What is the pH? By definition, pH is equal to the negative log of the hydronium ion concentration. We've got the hydronium ion concentration, so all we have to do is find our calculator, enter 0.85, hit the log button, and then change the sign. It's the negative log. So the pH is 0.07 06. No units on pH. Very low pH, like less than 1. Well, this is a strong acid, and I've got a pretty concentrated strong acid. So that would be the pH. Now let's look at how we find the pH of a weak acid. Okay, so now we're looking at finding the pH, and let's use the same concentration, right, that we just did for hydrochloric acid. In this case, hypochlorous acid, HClO. That oxygen influences how this acid behaves. It is actually a weak acid. So once again, it will donate the proton to water. It is an acid, so it's an acid. Water is again acting as a base by accepting the proton. What do I get? I get hydronium ion, and then after the acid donates its proton, the reverse reaction in this case can happen. The proton goes back. So in the reverse reaction, this is acting as a base. We call it the conjugate base. Or we would say once a weak acid donates its proton, what's left, that thing, is the conjugate base of that weak acid. So unlike the last time we said, okay, well 100% does that, and so I can just say, okay, 0.85 molar is going to give me 0.85 molar of hydronium, but in this case, no, 100% does not do that. Less than 1% will. So how do we find the hydronium ion concentration so that we can find the pH of this thing? We need to use an ice table. It's an equilibrium situation, so let's use an ice table. Here is my concentration initial. Some amount, I don't know how much, we have to determine that, will dissociate. Let's call it X. When X dissociates, we don't care about the change in water. We will get X amount of hydronium and X amount of the hypochlorite ion. So, let's say I've got my concentration. I'm going to leave Ka. Now, what do I have? 0.850 minus X amount of my acid. I've got X amount and X amount. Because Ka is such a small number here, the actual amount that dissociates, let's write the expression for Ka. Products over reactants. This expression comes out to a very small number. Therefore, I know that what I've got here is a lot less than what I got here. So the amount that dissociates to produce that is very, very small compared to 0.850. So that we can simplify our expression, let's say this approximates to 0.850. I've got 0.85 molar minus an insignificant amount relative to this number, so we can approximate. That makes this so much simpler to solve. We don't need the quadratic equation. Concentration of HCl, X. Chloride, X. Concentration of HClO, 0.850. And then we just solve for X, right? X squared over 0.850 equals 3.0 times 10 to the minus 8. Multiply both sides by 0.85 and then take the square root to find X. And the value I get is X, which is equal to hydronium ion concentration equals 1.60 times 10 to the minus 4 molar. So notice the difference, weak acid, strong acid. Strong acid, all of it was hydronium. Here, out of the 0.850 molar I had, only 1.6 times 10 to the minus 4 is hydronium. What's our last step? We want the pH. So our last step is take the negative log, and let's write it up here. We don't need our ice table anymore. Punch the log button and change the sign. I get 3.80 with some rounding. Does that number make sense? Looks okay to me. So it's a weak acid, but it's still acidic. Look at that pH, well below 7. But of course, the last one, with a strong acid, we had a pH of less than 1. Now, because this is only partially dissociates, our pH is 3.80. So finding the pH of a weak acid, we just run the ice table, we plug in to the expression for Ka, find the hydronium, and then take the pH.